Okay, everyone. So here I'd like to show a simple class demonstration for Chapter 3. And we will talk about sort of estimating diffusion coefficients using maximum likelihood. So if we remember in the presentations earlier, when we were using slides, we talked about sort of writing down a likelihood for Brownian motion, and then ultimately maximizing that likelihood in order to be able to obtain diffusion coefficients. So here we're going to obtain diffusion coefficients in two different ways. We're going to use a numerical routine within Python, kind of a black box routine within Python to maximize the likelihood. And we will assure ourselves that this optimization routine returns the same result that we would obtain by taking the derivative of our likelihood with respect to the diffusion coefficient and setting that equal to 0. And of course, we can compare all those things to the ground truth because we're going to be generating our own data. So let's get started. We import, of course, numerical Python, the math package, and an optimization scheme. So here are some parameters that I need in order to be able to generate my synthetic data. I specify the time between the delta t between my time steps, tn and tn plus 1. I define what I want my ground truth diffusion coefficient to be and how many data points I want. And then what I'm going to do is that I'm going to generate an array, or I'm going to sort of, generate an array of zeros, an array that I'm going to pre-populate with zeros of the size of the number of steps. So first things first, I'm going to select my first position for my particle. And then afterwards, I'm going to generate my synthetic data. So I'm going to start drawing my various subsequent positions using the diffusion coefficient that I've specified here in 5. And of course, I remember the formula that we had talked about in terms of the subsequent position being equal to the old position plus the jump size. And the jump size is the square root of 2 multiplied by the diffusion coefficient in the time step and multiplied by a Gaussian random variable whose mean is 0 and whose variance is 1. Finally, what I'm going to do is I am going to consider what the square sum of my positions is, in other words, the variance, and use that in order to be able to define the maximum likelihood diffusion coefficient estimate. So if we remember in the presentations when we took the derivative of the entire likelihood with respect to the diffusion coefficient, we ended up with an expression which was proportional to, or was equal to, in fact, the variance, the sum of these squared positions divided by 2 times the number of steps, the total number of data points multiplied by the number of steps. This was our maximum likelihood estimate. So I can at the very least, right now from this very simple code, compare and print out the ground truth diffusion coefficient, which I expect to be 5. I've specified to be 5 in my simulation, and what my maximum likelihood estimate is. Now, I don't expect my maximum likelihood estimate to be precisely 5 I especially expect it to deviate strongly from 5 as the number of data points that I consider is pretty small. So as I increase the number of data points, eventually I should obtain something which looks like it's converging to 5. Well, that's one way of obtaining the maximum likelihood estimate, and that's super convenient because I have an analytic form for the diffusion coefficient, the maximum likelihood diffusion coefficient point estimate. But I could also, in principle, compute the likelihood, using 3 explicit terms. So if I break down the log likelihood, I see that I can rewrite it as 3 separate terms, and then use a optimizer within Python in order to be able to maximize that likelihood with respect to the parameter d. I just need to be a little bit careful to specify bounds over which to look for my local optima. And now, of course, I can then compare this result that I obtain with my previous exact result, the ground truth, and my maximum likelihood estimate. So here we are. The ground truth was 5, we know that. And the other two estimates are not exactly equal to one another because, again, there's precision error, numerical error, involved in the numerical routine for optimizing the likelihood, round-off error. Same thing goes for the exact formula for the maximum likelihood estimate. But what we see is that they're pretty close. So now we can rerun this. 2,000 is a lot of data points, so we can reduce this, for example, to 20 data points. 20 data points is not going to be a lot of data points to estimate a diffusion coefficient. So we can go ahead and try to run this. Ground truth should still be 5, but the two estimates for the likelihood maximization should be similar to each other because they're both maximizing the same function. But they should probably deviate quite a bit from 5. So let's make sure to take a look. And here we are. They are both quite similar to one another, as we would expect, but they both deviate from 5 substantially. The fact that they underestimate 5 is not particularly relevant. They could have overestimated 5. What we're seeing is a bad estimate of the diffusion coefficient simply because our parameters, or simply because we had finite data. So if we run it again, and there's no guarantee that it's going to overestimate, but we get something which, yeah, still underestimates. We can try one more time, and this one here slightly overestimates. If we try just for fun, we find something else that slightly overestimates as well. So a lot of, how good we are at estimating the diffusion coefficient ultimately depends on sort of the random number generator that we invoke here, the C, in generating our synthetic data. So in other words, the random number generator that we generate here and then add to our positions in order to estimate or in order to simulate our Brownian motion. And that is ultimately where the sort of small finite size effects of the data come from. So if you wish to explore in the remainder of Chapter 3 for the online demonstrations, we kind of demonstrate a couple of the optimizers we've discussed in the advanced portion of the chapter, in addition to the Newton-Raphson, which we also sort of demonstrate as well. Thank you.